No questions? All right, let's continue with the problem we were doing last time, which was the two copper ones plus the tin 2 yields the two copper 2s plus the tin 4. And we set this up and tried the simplifying assumption, but it failed, right? And so what we can do is we could solve that previous equation for successive approximations, or we can do one little trick that might make successive approximations easier, or we might actually be able to solve that problem otherwise. And that is, we're going to reset this. The purpose of this is to eliminate binomials. We might only be able to eliminate one binomial, but the fewer the binomials there are, then the easier it is to plug in the equation. And so when we reset this, we're going to assume it's going to go all forward or all reverse. The way we determine which way we want to go is by looking at Kc and seeing which side it favors. If you look at that Kc, it's 1.48, so it favors the product just slightly. 1.48 is close to 1, so it's pretty well balanced. Just it's slightly biased towards product. And so what we're going to do here is we're going to reset it to the right. And so what we have, when we do this, is we assume 100% forward reaction. Assume 100% forward reaction. And so this would be like doing a Chem 1A stoichiometry problem, Chem 1B style. And so doing it, here we get minus 2y minus y plus 2y minus plus y. And so the new initial will look like this. We got to figure out which of these two is the limiting reagent. And looking at that, can you tell just by sight, is it the copper or the tin? Copper. This copper. And so we lose the limiting reagent completely. And so that's going to be consumed. And so this tells me that 2y is equal to 0.100. And so if 2y is equal to 0.100, then y must equal 0.100 divided by 2. Yeah. And so this is minus 0.100. This is minus 0.05. And so here, 0.300 minus 0.05 is going to give me 0.250 molar. And then this is going to be plus 0.100, so this will give me 0.300. And this will be 0.05, so it will give me 0.250. All right, so these are my reset initial conditions. And does everybody see how I did those? Yeah. Okay. All right, now the change. We don't have to calculate a Q. We can figure it out. How? Q is not necessary because if we have 0, can we go below 0? No, it has to go above 0. So we cannot lose from 0. We have to gain. And so this is going to be plus 2x. And so whatever side there are zeros, that's the side we're going to go to. And so this will be a plus, plus, minus, minus scenario. And so this will be plus x molar, minus 2x molar, minus x molar. And so at equilibrium, I'm going to have 0 plus 2x, or just 2x, actually, I don't need the 0. So just 2x molar, 0.250 plus x molar, 0.300 minus 2x molar, 0.250 minus x. And so what we can do is take these and then plug them in here and see if the math is a little bit easier. And so 0.300 minus 2x squared, 0.250 minus x divided by 2x squared and 0.250 plus x. And so it eliminated one binomial, but still it doesn't look easy to solve because it's fourth order equation, right? X to the fourth, or not fourth order, sorry, third order, x to the third. And so it looks like we still have to do successive approximations, but you know, since we set it up like this, we might as well try the simplifying assumption. I have a feeling the simplifying assumption won't work because this should be a 1-to-1 ratio. And so I kind of expect a significant or more significant change back, but anyway, it doesn't hurt to try it. And it doesn't take that much time. And so if we do the simplifying assumption, we're assuming the change is small. Compared to the initial. And so what would constitute a small change compared to the initial? A small change compared to the initial would be like if you had a swimming pool of water. If you have a swimming pool of water and you remove a drop of water or you add a couple of drops of water, is that going to make any difference at all? No. And so this would be like if I had a swimming pool, I'd take 2 drops, no difference. Here, same thing, you know, a little smaller swimming pool, but still a big swimming pool minus a drop. Swimming pool plus a drop. Here, this is not a swimming pool. I'm adding 2 drops to nothing. If I add 2 drops to nothing, is that significant? Yeah, that's significant. Everything's significant compared to 0. That would be an infinite % change. And so here, now, do I have to say, oh, 2x is much smaller than 0.300, x is much smaller than 0.250, x is much smaller than 0.250? No. What I do is I'd look for the biggest % change. Which of these 3 would have the biggest relative change? Is it 2x compared to 300, or is it x compared to 250? The easiest way to do that is just to level the playing field. So either I'm going to divide this by 2 or I'll multiply these by 2. I'll just multiply these by 2. And so the change here would be a 2x change for 500, whereas this would be a 2x change for 300. And so 2x change for 300 would be a bigger relative change. Does that make sense? And so here, what I'm going to do is I'm going to make this assumption. I'm going to say that 2x is much smaller than 0.300. If this is true, then it's got to be true that 2x is smaller than 0.500, right? Because if I doubled this, that's the way it would be. And so assume the change is small compared to the initial, and so what we're going to get is this. If I have a swimming pool and I lose 2 drops, but how do I know it's 2 drops? Because I don't know what x is. That's true, you don't know what x is, so you're just going to go ahead and pretend it's going to work. And if it doesn't work, we'll know because when we get our x value might come out to 50,000 gallons rather than 2 drops. If it comes out to like 50,000 gallons, then it's a significant change. And so we're going to pretend it works, so therefore it's not equal, it's just, you know, kind of equal to this. 0.300 minus 2x is just going to be 0.300, so it's going to be squared. 0.250 minus x will be 0.250. 2x compared to 0 is significant, so we'll leave that here. 0.250 plus x will just be 0.250. And so that cancels. And then we solve for x. Now the math is much easier. So this is the simplifying assumption, but will it work? Let's see if it works. And so we solve for x, and x will come out to Does somebody have it? 0.123. Okay, did you take the square root too? Okay, so 0.123 is what we got. And so now we made this assumption and then we calculate what the x is. It's 0.123. We have to justify the SA. And when we justify the SA, we calculate the percent change, the biggest percent change. And so we only have to do one of those, the one with the largest relative change, which would be the 2x to 300. The percent change is equal to the change over the initial times 100%. And so the change is going to be 2x. So 2x is going to be 0.246 over the initial. The initial is 0.300 times 100%, which gives us what for a percent change? 82%. What's our cutoff? 5%. 5% is even too big. And so this is way bigger than 5%. In fact, you know, if I said I'm losing a drop of water and you say, well, okay, and then you take 82% of the water out of there, is that a small change? No, even though this answer is not correct, you know, it's going to be ballpark, and so it's not even close. So the essay fails. The simplifying assumption fails. And then you say, well, we just wasted a lot of time doing the simplifying assumption. The truth is, the simplifying assumption doesn't take much time. You know, when you do it, it takes very little time, and most of the time it works. So if it works, you're going to save a lot of time in the long run. But sometimes it fails. But even though it fails, it's not wasting time, because in order to do successive approximations, you have to make an educated first guess. And so normally what we do is we just take the number up here, let's say 0.1, and call that our first guess. You know? And so the SA fails, we have to do successive approximations. And doing successive approximations of an equation like this is a little bit simpler because we have one less binomial. And so we'll take this, like this is wrong, and then we'll do successive approximations. And then we're going to guess. You know, our first guess is that x is equal to 0.1, and then we'll check our k value, see how close our k value comes to 1.48. Okay, any?
I don't understand what you mean when you reset the binomial to eliminate.
Oh, to eliminate the binomial, reset. When you reset the initial conditions, you get zeros. Well, for example, the copper was 0.100, but that was our limiting reagent. And so when we reset this, it went from 0.100 to 0, because we consumed 100% of our limiting reagent. Now when you do the change is plus 2x, we end up with 2x, versus if we hadn't reset. If we hadn't reset, we got plus 2x, and then we have 0.100 plus 2x. And so what I mean by get rid of a binomial is, up here we had a binomial that we had to square. Down here we don't have a binomial that we have to square. And so it just is a little bit easier in terms of calculator, pushing the keys on the calculator. But it didn't really make that huge of a difference, because, you know, the other equation would have worked too. The other equation would have had 4 binomials, and this one just has 3 binomials. And so just a little bit easier, but you know, it didn't take that much work to do, so that's why it's worth going.
So we reset all of them, the products and reactants, to 0 and use this?
No, we don't reset all of them to 0. What we do is we look at what the limiting reagent reagent is. And we do a Chem 1A stoichiometry, but we don't do it like we normally do a Chem 1A stoichiometry. When you normally do it, you figure out what the limiting reagent is, either by comparison of moles or by the smaller amount method, and so smaller amount of product. And so in this case, we just do it in our head here. And so if I had 0.100 and is it 300? 300 molar. And I look, well, I can see what the limiting reagent is going to be. It's going to be my copper. And so Chem 1A tells me that the limiting reagent is completely consumed. So after this reaction, I'm going to be left with 0 molar limiting reagent. How much excess reagent remains? Well, the amount of excess reagent that remains is the amount initial minus the amount consumed by the limiting reagent. And that's going to give you the amount of excess reagent consumed. And so we could figure it out because this was minus 0.100. And therefore, this has got to be minus. If we lose 0.100 of copper, then we need half of it. And so this is going to be minus 0.050. And so rather than doing a stoichiometry, we just do it in our head like this. And so we call this minus 2y. We call this one minus y. So we get minus 2y minus y.
Will we ever have problems where it's not half, like maybe 3 or 4?
Yeah. Right. You'll have problems where it's like 1/3 or something.
And that we just determine by looking at the coefficient?
Yeah, just at the coefficients. This is a 2-to-1 ratio. So if we have 0.05 tin, then we need double that for copper. But we can't go above 0.05 because we run out of copper. And so when we reset, we just assume either 100% forward reaction or 100% reverse reaction. And then start from there. Okay, other questions on this? Now, the successive approximations, I'll let you finish that. So, for chapter 15, just the Chem 1B stoichiometry is a little different than Chem 1A, actually a lot different. You know, and what we do in Chem 1B stoichiometry is we use K, right, to determine the outcome of a reaction. And so K is just equal to, generically, we have Kc, which is just the product over the reactants. G, concentration, raised to little g, h, dot, 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 A, little a, B, little b, dot, dot, dot. So that's Kc. We also have Kp. Kp, rather than using molarities, we'll put in atmospheres or bars here. Essentially, it just works the same way. The units are just different. And so we could use these, we call this the law of equilibria. We could use the law of equilibria to figure out what the stoichiometry is going to be. And so K is very important for us. We need the numerical value, you know. What is the number here? That number is going to tell us the ratio. Okay. And so what we wanted to figure out is this, you know, what are all the ways to determine the numerical value of K? We'll just say ways to determine K. The first way is we just run a series of experiments. In other words, we just do observations. So we started off with a tin and the copper reaction. We got 1.48, 1.48, and 1.47, and just average those. We had numerical value of K of 1.48. But do you have to do experiments and take observations for every value of K? No. There's ways that we can avoid doing any experimental work. And calculate the value of K. The calculation for the value of K is similar to Hess's law. Do you guys remember Hess's law from Chem 1A? Like, you want an unknown delta H. You know, if you want an unknown delta H, you could do a calorimetry experiment, but do you want to have to do a calorimetry experiment for every? No. And so we learned some things like, we're going to have things that are similar but quite a bit different. And so, for example, if we multiply our reaction by some coefficient n, and so let's say we double it or cut it in half, what does that do to our K? Does it stay the same? Well, our delta H would change. You know, if we burn a mole of methane and we decide to burn 2 moles of methane, we're going to get twice as much energy. Or if we burn a half a mole, we're going to get half as much energy. And so for K's, it works a little bit different. Rather than NK, that is, we just double K or cut K in half, we raise it to the nth power. And so it'd be just K to the n. If we reverse the equation, we go GG plus HH plus dot 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 AA plus BB plus dot dot dot. What would we do to the original K value? Yeah, we normally, for Hess's law, we would change the sign. So we would go negative, right? But not for us. What we're going to do is we're going to take the reciprocal, which is be 1 over the K. If you sum up equations, let's say I have equation 1 plus equation 2. This would be like Hess's law. We have a K1 and a K2 for equations 1 and 2, and then we get equation 3, which is the sum of the two. Equation 3 is going to have a K3. Is the K3 going to equal K1 plus K2? That's what we do in Hess's law. We just add up the delta H's. Is that what we do here? No, here we wouldn't add them up. Here we're going to multiply the K. So it would be K1 times K2. And so this does is it saves us from doing some experimental work. If we can calculate it, then it's going to be much quicker and much easier to determine. And so there are other methods. Actually, these other methods are even easier, but these other methods aren't going to come until chapter 20. So we'll wait until we get there. Chapter 20 deals with thermodynamics. All right, so just some methods for calculating K. In chapter 16, we're going to continue doing ice calculations, acids and bases. Except one of the big differences between chapter 15 and chapter 16 is that we're going to have multiple equilibria occurring simultaneously. And so let's start off with an example of chapter 16 style calculation. And also we're going to learn some stuff about acids and bases, but let's just look at the calculations first. And so a calculation would be something like this: 1.0 times 10 to the minus 8 molar HCl. In chapter 8, we want to calculate the pH. pH will tell how acidic or basic this is. Typically, when we calculate pH, we use this equation. The pH is equal to the negative log of the H plus concentration, or the negative log of the hydronium ion concentration. For the reactions review, I've been using H plus. I use H plus because it takes up less space and less writing, and it's a lot easier. You don't have to deal with hydronium. But in chapter 16, we're primarily going to be expressing it as hydronium. H plus itself is too unstable to exist in water. H plus is just a single proton, and it's very reactive. So have you done calculations like this before? No? Never?
When you're talking about log,
Oh, but not pH? All right. pH, P stands, it's a power function. This is the power, actually it's a negative power. The negative of the power, so we'll just say negative power of the H plus concentration. And so it's a power. So conceptually, it's just like this. If we look at the H plus concentration here, which would be the same as the HCl concentration. HCl is a strong electrolyte. If we look at the H plus concentration here, what is the power of the H plus concentration? 8, negative 8, right? And so if we take the negative of the power, the pH should be 8. You can plug it into this equation and see. Just take this concentration and plug it in here or here. Because HCl is a strong electrolyte, so it should break up into H plus and Cl minus. And so if you have 10 to the minus 8 molar HCl, you're going to have 10 to the minus 8 molar H plus. It doesn't make sense? Why not?
If it were an 8, it'd be more basic than 1.
All right. Well, yeah, you know, there's something else you should know about the pH scale. So let's take a look at what the numbers mean here. But the calculation's simple, right? The calculation is that the pH, after you plug it in, take the log of this and then just change the sign, it comes out to 8. Let's talk about power functions, though, in terms of sig figs. In terms of sig figs here, we have 2 sig figs here. How many sig figs do we have right now? Is that 1 sig fig?
No.
Okay, so is that 2 sig figs here? Actually, no, this is not 2 sig figs. Is this 2 sig figs now? Yes, this is 2 sig figs, because in power functions, everything in front of the decimal is not significant. This 8 just represents this, the power of the exponent here. But this stuff that comes after the power is related to the coefficient. And so this is actually 2 sig figs. And so when you're dealing with power functions in general, the way we count sig figs is after the decimal. Before the decimal is what we call the placeholder, the decimal placeholder. All right, let's talk about the pH scale. What does the pH scale range from? It ranges from what to what? It ranges from 0 to 14, and then right in the middle is 7. 7 we call